Hello and welcome to class. My name is Cindy Shelton. I'll be your teacher for this applied math class, and I'm hoping that you'll be able to utilize your notes that's inside of your Blackboard shell. You can print those off or follow along online if you open those up. So that's what I'm going to be using from. So we're going to start with chapter 1 now. The first chapter that we cover, it's critical thinking, skills, and logic. And it's in your first module. So the first thing that you'll notice is it says that we will study in 1.1 inductive and deductive reasoning. Alright, so we'll start with the inductive reasoning. And there's just a little difference in the two, and you'll see this. I'm going to read with you along here. It says, inductive reasoning is the process of reasoning to a general conclusion through observations of specific cases. This type of reasoning is based on patterns and expectations. You can't actually prove it. When forming a general conclusion using inductive reasoning, you should test it with several cases to see whether the conclusion appears correct. If a special case is found that satisfies the condition of the conjecture or hypothesis, but produces a different result, such a case is called a counterexample. Only one of these is needed to show the conclusion is not valid. If a counterexample can't be found, the conjecture is neither proven nor disproven. Okay, so an example, that'll help, right? An example, here's a conjecture. Two even numbers multiplied together will always produce an even number. That seems reasonable. You probably think that seems like that would be true. So we'll look at some examples, some observations. An even number times an even number. For example, 2 is an even number times 2 equals an even number in that case. 2 times 4, an even number times an even number, equals 8, an even number. 6 times 8. That's looking pretty good. But, I mean, we could do this all day long and never prove this to be true in this way. This is just, like I said, inductive reasoning. It just looks like it's true from these specific cases and observations. But again, we haven't proven anything. But it's looking, from these examples, we could keep on going. Looks like that's true. So from our observation, this appears to be true, but with what we have, we can't prove it, and for all cases. Thus, we might predict, though, by inductive reasoning that our conjecture is true. Another example would be fingerprints in your DNA. Those are thought to be unique. You know, we expect those are unique, kind of accepted that is true, but it can't be proven. They just have not found two that are alike yet. But it looks like everybody has unique DNA and unique fingerprints. But again, we're still basing that on observations so far. That has not been absolutely proven. So here's an activity for you to try, something that might look like what you'll see in your homework. So when we get to the activity portion, feel free to pause the video. That's what I want you to do. Pause the video, take your time to do the activities, and then jump back on. I'm going to keep on rolling though, but you use your pause video. Pause of the video. So the first one, we have 1, 4, 9, 16, 25, and it says predict the next number in the sequence. There's no way to prove what the next number in the sequence would be. Again, with inductive reasoning, we're not proving anything, but just based on the pattern, what does it look like? So you could argue this with me, but the pattern that I'm seeing, these are the perfect squares. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, so the next one would be 6 times 6, 36. Based on the pattern, I expect that to be 36. The next one in the activity, this is one of my favorites. It actually has a name called the Fibonacci sequence. And so I don't know if you guessed this one or not when you were looking at it, but they're adding the two numbers beforehand. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, so the next one should be 8 plus 13 is 21. So that one was 21. And again, this is called the Fibonacci sequence. You can look that up, maybe Google that. And it's a neat sequence. It actually shows up in nature, in pine cones, daisies, the number of petals and spirals. Actually, there's a lot of things in nature that follow in the Fibonacci sequence. So you might want to look that up a little bit more. Okay, the next one, 8, -4, +2, -1, positive 1/2. So one thing that's happening is the signs are alternating, positive, negative, positive, negative, positive. So this one should be negative, and they're also halving each time. 8 divided by 2, divided by 2, divided by 2. They're halving, so a half divided by 2 is actually a fourth. So -1/4 should have been the next number in that sequence. All right, moving on. Next activity. It says pick a number, multiply it by 4, and add 2 to that product, and so on. So it's got a list of rules for you to do, and then repeat that. So again, pause the video and do that. I'm going to go ahead and do an example. My number I'm going to pick is 7. It says pick any number, so I'll pick 7. Multiply it by 4 is 28. Then it says add 2 to that, which would be 30. Divide that number by 2, which is 15. Subtract 1, 14. Do it again with some other examples. So I'm going to do the number 8. Do it again. 8 times 4 is 32. Add 2 to that is 34. Divide by 2 is 17. Then it says subtract 1, 16. So I've not done enough examples to really establish a pattern. You should keep doing this over and over again. So maybe try it with 9. Maybe try it with a negative number, fraction. Try it with multiple examples. But it looks like the number I started with, 7, turned into a 14. And here the number I started with, 8, turned into a 16. It looks like the numbers might be doubling with this little procedure. So that's the conjecture I would make. It looks like the relationship is that the number doubles. All right, we have another example of that, number 3. So go ahead and work through number 3. Pick a number. I want to pick 7 again. Again, this is example activity 3. Multiply my number by 3, which is 21. It says to add 6 to that, 27. Divide that by 3, which is 9. Then it says subtract 2 from that, which is 7. So it looks like I came out with the same number this time. That might be my conjecture, but again, you need to do more examples. So I'm going to take the number 8. Multiply it by 3. Add 6. Divide that by 3 is 10. And then subtract 2, which is 8. Same number. And again, to be realistic, you need to keep on doing that. Try it with a few other numbers to establish the pattern. But it does look like that the number comes out to be the same thing. Again, I'm not proving anything, but it just looks like it. And again, that's inductive reasoning. You're not proving, but just based on patterns, it looks to be so. Number 4, mysterious math. Now, I found this example on a wall in a frame at the Ripley's Believe It or Not Museum in Gatlinburg one time, and I thought it was interesting. So take a minute and read that example. Tells you to think about the number of living brothers that you have. I have 4 brothers. Your sisters, I have 1 sister, and then living grandparents, I do not have any living grandparents. So those would be my numbers, but everybody would have something different maybe here, but it should work for all of us. So it says take the number of your brothers, which for me it's 4, and multiply that by 2. It says add 3 to that answer, which is 11. Multiply that by 5, which is 55. Add my sister, 56. Multiply that by 10. Lots of steps here. 560. Add your grandparents. I have none. And then subtract 150 for some reason. All right, and it works out to be my numbers. 4 brothers, 1 sister, 0 grandparents. And it should work for all of us. We're going to prove it with deductive reasoning here in a little bit, but just doing with inductive, we just do example after example. So everybody in the class, you do your own scenario with your brothers, your sisters, and your grandparents, and see if this doesn't work. Should work for all of us. All right, now we're going to find out why this works. We can then prove it by deductive reasoning. So the next type of reasoning, deductive, if you'll read with me on down, it says Second type of reasoning process is called deductive reasoning. Mathematicians use deductive reasoning to prove a conjecture true or false. Deductive reasoning is the process of reasoning from the general case to a specific conclusion. We use a variable x, so we get into kind of the algebra domain there. General case would be just x, meaning any number. X can represent any real number. And we put that into the equation, and then we do some algebra magic to it and show that it always works for all cases. So we can do all the examples we just did. We can go back through those, example 2 through 4, and we can start with x being the number instead of a specific number. You might remember whenever I like the number 7, so I started with 7 on my examples. So instead of picking a certain number, a specific number, I'll pick a general number, x. So it says pick any number x, multiply it by 4, so 4 times x. Then add 2 to that product. Then divide all of that by 2 and then subtract 1. So we can actually do a little algebra magic to that and say both of these are divided by 2, so that'll divide that out to be a 2x and divide that out to be a 1. So we can reduce that to 2x plus 1, and then whenever we incorporate the minus 1, those cancel, 2x. And that's why on that first example we talked about, it always wound up being double the number. Every time the any number that we pick, x being any number, is then times 2, it just doubles the number by going through this procedure. So that would be deductive reasoning proving it. And then we can do it for the other example. So again, pause the video. That was actually activity 5. It was the same one there that we just did. So try example or activity 6. See if you can pick an x and go through and do it algebraically. Okay, so when we pick a number x on activity 6, multiply that by 3, add 6 to it, divide that by 3, and subtract 2, we could reduce this down. The 3's divide to just be 1x, and the 6 divides by 3 to just be 2, and then minus 2, those cancel. And so every time you start with the number x, you do this stuff to it, it comes out just to be the same old number x. So that proves it, why it was working out that way. We can also do it on activity 7 with the grandparent, brother, sister example. We can multiply our numbers of brothers by 2. Okay, now there's 3 unknowns here. Your brothers, how many brothers you have, how many sisters, and then your grandparents. So we'll let these be different variables because they're probably different values. We'll call this X, Y, and Z, or A, B, C, or whatever letters you like. So this one's a little more advanced and probably more algebra than we'll get into in this class, but just for the fun of it, we'll do this. It says take your number of brothers by 2, so it'll be 2x, add 3, multiply all of that, so I do need a parenthesis, multiply it by 5. I need to distribute there, that would be 10x and 15. Then add your sisters, which would be y. Then multiply all of that by 10. So again, I need to distribute everything times 10. There's where that 150 comes in, that weird 150 we saw. Add your grandparents, which is z, and then subtract 150. So that weird 150 that wound up in there kind of gets canceled out. And then we have 100 x's, 10 times y, and then the 1z, which makes your brothers be in the hundreds place, your y's, your sisters be in the tens place, and then the z, your grandparents, be in the ones place. So it works out just perfectly there. So that's kind of an overview of inductive, deductive reasoning.